Welcome back. So this is lecture 43 in this course on Bayesian modeling. The topic of today's lecture is logistic and Poisson regression with BRMS. Right? So we are going to see how we can implement logistic regression model and a Poisson regression model in the Bayesian framework using BRMS package. Right? But before that, I will briefly talk about these two types of regressions. Right? So far, you know well about Gaussian regression, right? So, and we have also implemented in BRMS, right? We briefly discussed logistic regression. So, let us take a look at it again. So, suppose we are interested in modeling when participants see a word on a screen, okay? Let's say a string, any string on a screen, they need to recognize whether it's a proper meaningful word or not. So, if it is not a meaningful word, they will answer with no. If it is a meaningful word, they will answer with yes. Right? In this case, for example, it's no. It's not a meaningful word. They should answer with no. What we are recording is their response in each trial, whether they make a correct response or an incorrect response. Okay, so correct response will be encoded as 1. Incorrect response will be encoded as 0. That's the task, and that's our outcome variable that we are recording. Okay. So, if I want to model these responses, 0-1 responses, a usual strategy is this. So, I can define a Bernoulli model for this. So, let's say response in ith trial comes from a Bernoulli distribution with underlying probability of producing correct response theta, where theta has some prior on it. So, let's say beta 80-20 or something like that. Okay, fine. But what if someone claims that on average the words with high frequency are recognized more properly or recognized more accurately compared to low frequency words. So, if there is a high frequency word, people are going to recognize it more accurately compared to low frequency words, right? So, whenever you get words like book, table, people are more likely to be correct in recognizing them rather than more difficult words, because people might confuse it with some known word or they may think this is not a proper word, right? So, that's a reasonable hypothesis. So, hypothesis is this, that high frequency words will be recognized more accurately on average. Okay, so that's our hypothesis. How do we encode this hypothesis and what does it mean? So, let's say theta is the parameter that indicates probability, the underlying probability of correctly recognizing a word, right? So, this is basically accuracy of recognizing a word. What we are saying that on average this accuracy increases as the frequency of the word increases. Okay, so we can do this using a regression model. So, let's say response in the ith for the ith word comes from Bernoulli theta I, where theta I is the accuracy for the ith word, and theta I is a function of frequency itself. So, let's say theta equals to alpha plus beta into frequency I. Okay. So, you can write it like this. But the problem here is this, that theta I has to be strictly between 0 and 1, and alpha and beta are parameters. Frequency can take any value between, let's say, 1 and 7. So, it will be very difficult to control that theta I has values between 0 and 1, because alpha and beta has to be estimated, right? And let's say, and how the HMC sampler work, you know. So, basically we have discussed this earlier, right? MC and HMC samplers, they propose different values of alpha and beta, right? So, you generate proposals for alpha and beta, and then you evaluate the likelihood and prior and see if these values for alpha and beta are in higher posterior density region or not. What if you propose values of alpha and beta like this? Alpha is 0.7, beta is 0.8, and value of frequency is 2. In that case, what will be value of theta I? 2.5, or I think 2.3, but that's going over 1. Okay, So that means you're going to waste a huge number of samples that are going beyond, for which the value of theta is not between 0 and 1. Okay, so that's a very useless kind of a strategy if you do this, right? So this is a serious problem. That means basically we need some transformation that can keep theta between 0 and 1 strictly, such that you can allow an alpha and beta to be anywhere between minus infinity and plus infinity, but still the value of theta remains between 0 and 1. So if you can apply some transformation, something like this, inverse logit of alpha plus beta into frequency I. So if you write it like this, the same function like this. So rather than writing it as a linear function of frequency, I write it as an inverse logit, a sigmoid function of frequency. It looks like this, right? Now, regardless of what value of alpha and beta you take, whether they are towards large negative values or large positive values, doesn't matter what value of alpha and beta you have, theta will always be between 0 and 1. Okay, and this is the kind of relationship you get between theta and logit theta. So let me draw it here. So if this is 0, this is 1, you have theta on x-axis and logit theta on y-axis, or the other way around, let's say okay, fine, it's inverse logit here, inverse logit of alpha and alpha here. So let's say alpha can take any values between minus infinity and plus infinity. Okay, the value of inverse logit would be strictly between 0 and 1. So let's say here is 0, here is 1. It looks like this. Okay. Anyway, the another way to write the same equation is like this. You can write logit of theta I equals to alpha plus beta into frequency I, right? So the relationship between theta and logit theta is like this. So at 0.5, value of logit theta is 0. As you go towards 1, logit theta increases almost linearly and then sharply increases near 1. Here as well, decreases linearly and sharply decreases near 0. This is how the relationship looks like. But the logit theta can take any value between minus infinity and plus infinity. So when you apply this transformation, it allows these things to have values between minus infinity and plus infinity. Okay, so that's the point. So how we write logistic regression finally? That response in ith trial comes from, let's say, a Bernoulli distribution with underlying probability of success theta I, or probability of correct response theta I, where logit of theta I equals to alpha plus beta into frequency I. Okay, now this is how you can write a logistic regression. Okay, so let us see this in R. Okay, I've already done some Gaussian regression. So let me first generate fake data for accuracy, which depends on frequency, and then I will fit a logistic regression model. Okay, I can actually use same values of frequencies that I had earlier, right? Now I just need to generate theta, a vector of theta from these frequencies, which would be, so this is actually sigmoid function or the inverse logit function, and parameter alpha beta t into frequency. But what is alpha t and beta t? That you will need to define. So let's say alpha t is say 1 and beta t is 0.1. Okay, so let's see what kind of theta values I get with this. Okay, So I can increase the intercept. This is better. Okay. Okay, so let's do with this. Okay. Now we will generate accuracy data. So I can use the for loop in the same way, and then I create a data frame. Response in the ith trial comes from a Bernoulli distribution, sample size 1, and probability theta being theta I. Now I can record, along with RT, I can record response. So if you visualize response, it's like this. Okay, so now you have data containing recognition times as well as responses 0 1 0 1 as a function of frequency. So I've generated fake data of that sort. Now a model is like this: Bernoulli theta I, where logit of theta I equals to alpha plus beta into frequency I. Okay, so the parameters of interest are now alpha and beta, not theta. So let's say for alpha, you set up a prior. Now alpha is on logit scale, right? So you can set up a prior like this. Let's say 2 1, okay, or 2 2 is fine. And for beta, you set up a prior like this, normal, it's a 0 1 or so. So this is your model now. Okay, so let us fit the model. Now here the change will be response is predicted by frequency, not just 1 plus frequency. This is intercept, and this is main effect of frequency. And data is det, family is Bernoulli, good. For intercept, the what you're defining as intercept is normal 2 2, that's a prior on intercept. You need to define prior on beta as well, so that you have defined normal 0 1 class equals to b, that's prior on beta, and everything else is same. Okay. So let us now fit this model. It's compiling. Okay. So in this piece of code, I have implemented a logistic regression model. So only change is this. Basically, the formula remains the same. Response is being predicted by frequency in the same way as we did for Gaussian regression. Here, of course, the family has to be now Bernoulli. Okay, and the priors you're defining are for intercept and slope, but they are on logit scale here. Okay, because you're defining alpha and beta on logit of theta I on this scale. So that's why the intercept is, we are defining is somewhere between -2 and +4, and beta is somewhere between -2 and +2. This is reasonable. It's quite uninformative, but it's reasonable. So it is started sampling and it's done. It was very fast. So let us see. Let us inspect the chains first. Chains are mixing well for both intercept and the effective frequency. And let us see the summary statistics to check how well we are doing in parameter recovery. Okay, so these are estimates. So for the intercept, we are getting 95% credible interval between 2.5 and 2.97. The actual true value that we took was 2.5, so this recovery is good. For frequency, the 95% credible interval is minus 0.34 to minus 0.25, which is also good because the actual true value was 0.25, right? So parameter recovery is good. And is there an effect of frequency on accuracy? Yes, so data seems consistent with the effect of frequency on accuracy. The data suggests that there is a effect of frequency in such a way. Oh, why it is negative? It's supposed to be positive, right? Okay, we made a mistake here. Yes, it should be alpha plus beta t into frequency. Okay. There's a mistake in data generation. I think it should be fine now. Yeah. So, but this is how you fit a logistic regression model. You can see the output again for this model. And then we can go to Poisson regression model. So this is the basic template that we will use multiple times for regression modeling, and we will of course you will do logistic regression model a lot. They have applicability across disciplines, so you might find them useful even for machine learning models and other data for other data analysis that you will do apart from psychological sciences. Okay, so let me see again the summary of M2. Yes, so this time I get positive effect, right? So effective frequency is somewhere between 0.10 and 0.27, right? So the posterior recovery is good. So basically what it suggests is that as frequency increases, the average accuracy increases. Okay, so the data is consistent with the hypothesis, with the prediction that the effect of frequency on accuracy is positive, that as frequency increases, accuracy increases. But of course, again, to make some claim about whether there is an effect of frequency, basically about your hypothesis, or to make a claim about, or to make a claim that whether there is evidence for this effect. Okay, to make a claim about evidence, you need to do model comparison, right? So for proper hypothesis testing, as you do using t-test in the frequentist framework, in the Bayesian framework, you need to do a model comparison, okay, which we will of course learn later. But right now we are just looking at these 95% credible intervals, which tells you about true value of a parameter. Okay, so far we have done logistic regression. What about Poisson regression? So what if you are interested in modeling number of road accidents in a city? Okay, you are observing number of road accidents on every day. Okay, so let's say number of road accidents on ith day. Okay, so this is what you will assume. So let's assume it's coming from a Poisson distribution. So this is your likelihood assumption. Okay, so let's say number of road accidents on ith day comes from a Poisson distribution with underlying rate of road accidents being lambda, and then you set up some prior on lambda. So let's say prior on lambda is normal 50, 10 or something like that. Now, someone makes a hypothesis that road accidents are higher on weekdays because people want to reach their workplace as fast as they can and there is a lot of traffic. So, the number of road accidents is higher on weekdays compared to weekends, right. So, ith day can be a weekend or a weekday. Okay. So, we are going to test whether the rate of road accidents is higher on weekdays compared to weekend, right. So, how do we do that? Using a regression model. So, let us say Ni comes from Poisson lambda I. Ni is the number of road accidents on ith day. Lambda I is the rate of road accidents on ith day, because lambda is now going to depend on whether it's a weekday or weekend. So, let us say we write lambda is a linear function of alpha plus beta and linear function of weekday. So, whether it is a weekday on the ith day or not. Okay. So, by the way, this predictor will take value 1 if it is a weekday, it will take value 0 if it is a weekend, okay, or 1 minus 1, whatever you want to choose. Okay. So, if weekday, 0 if weekend. Okay. So, the model should predict a positive estimate for beta. So, your hypothesis predicts that beta should be positive. Okay. So, this is the prediction of your hypothesis, that beta should be positive, because if it is a weekday, the number of road accidents would be higher. Okay. Now, interestingly, you are in the same problem here, same technical problem, that this parameter lambda cannot take 0 or negative values. Okay. Lambda has to be strictly greater than 0. And if you leave it like this, then it is no way to control to have only positive values, because at any point alpha and beta can be proposed to be negative, and then it will be difficult for the sampling, right. So, how do we do this? How do we ensure, what kind of transformation we apply to ensure that lambda is always positive? Okay. So, the relevant transformation here is this, that you write log lambda equals to alpha plus beta into weekday. Okay. Let me write properly here. So, let me rewrite the whole regression. So, number of road accidents on ith day comes from Poisson lambda I, where log of lambda I equals to alpha plus beta into weekday in the ith trial. Okay. Now, another way to write the same thing is lambda I equals to exponent of alpha plus beta into weekday I. What this will do? Basically, you are taking exponent, so this value is always going to be positive, right? That is the point. So, this is how you can write it. Now, this will take care of that constraint that lambda has to be always positive. So, this is called a Poisson regression model. Okay. How do we set it up in BRMS? In the same way as you do set up a logistic regression, don't need to worry much about this. So, let us say this is the number of road accident and it is predicted by 1 plus this predictor weekday, then family will become Poisson, right. So, up to this point your likelihood assumption is complete. Now, you can define priors, and there are two parameters, alpha and beta. So, this is class intercept and this is class B. What will be the priors on alpha and beta? Now, alpha and beta are on log scale, by the way, because you are setting up this regression like this, that log lambda equals to alpha plus beta into weekday, right. So, that means when the value of weekday is 0, basically during the weekends. So, during the weekends, okay, so parameter alpha can be interpreted like this, that what is the log of rate of road accidents during weekends. So let's say during weekends, on average, road accidents are around 50, or let's say 100. It should be lower. So let's say 50 during weekends, right? Then alpha is somewhere around log of 50. So that's the range in which you should define alpha and beta, right? So for example, in this case, it could be somewhere around what it would be. So log of 50, you can check what is log of 50. So somewhere around 1 point, I don't know, 1.4 or something, somewhere around that. Similarly, you will have estimate for beta, which will also be on log scale. So it should be also somewhere around 0.5 or something. So you can define priors like this. So let's say on alpha, you define a normal 2 prior. On beta, you define a normal 0 1 prior. Okay, so this is a reasonable range. Okay, so you shouldn't define but in the range of 50 and hundreds, right? But that's not where alpha and beta are going to be now, because you're exponentiating them. Okay. So this is Poisson regression model. To implement it in BRMS, so basically let us generate a little bit of fake data in the same way as we generated here, and then we fit a Poisson regression model. So rather than frequency, now you generate weekday kind of data. So let's say this is C of repeat 100 times, okay, 500 times, and repeat 0 200 times. So that's weekday. Let's say alpha t is somewhere around, let's see, log of, what is log of 50? Oh, it's much higher. Okay, 3.91. Okay. So let's say true alpha t is 4 and beta is, let's say, 1. Okay. Now let us do this. Exponent of alpha t plus beta t into weekday. This will become your lambda. Okay, so this is good. So you've gotten your lambda. Now you generate number of road accidents. And I comes from R poise 1 lambda I. So now in data, you can store weekday equals to weekday, day equals to 1 to length of weekday, and here you have number of road accidents on ith day, so n equals to n. So this is your fake data. You can see how it looks like. Now what we can do, we can fit this using BRMS. So we will test the effect of weekday versus weekends on the on rate of accidents. So the outcome variable is n, dependent variable is n. Effect that you want to see was is of weekday. Data is dead. Family is now Poisson. By the way, it also shows you options. what kind of link you want to define. So for example, here I will define log link, which is basically the kind of transformation you want to apply on parameter lambda. Here you define the prior. So let's say this is the prior on intercept and this is the prior on beta. This is fine. So I'm running this model now. So here I've defined a Poisson regression model in BRMS. Right? Everything else remains the same. Only thing I changed is this family Poisson, right? And of course, the interpretation of these parameters changes because they are on log scale. So I defined these intercept and beta on log scale. Okay. So this is somewhere around log of 50. This is somewhere around log of to what rate number of road accidents increase from weekend to weekdays, right? So it's a log of that difference. Okay, so it has started sampling. Okay, it's done. Chains are mixing well, right? Posterior recovery seems good. Let us see the summary. Okay. So this is how the effect of weekday looks like. So 95% credible interval is between 0.98 and 1.01, which suggests there is a positive effect of weekday. So if it is a weekday, the number of road accidents is likely to be higher, right? Is there evidence for this positive effect of weekday? That we cannot say based on this. For that, we need to do model comparison. What we can say based on this, that the data are consistent with your prediction, because you predicted that the parameter beta will be positive, right? That's what your hypothesis predicted, right? And for intercept, you can also see 95% credible interval, 3.99 to 4.02. Yeah, so the parameter recovery is good because the true parameter value was 4 for intercept and 1 for weekday. All right, so this was Poisson regression model. So in this lecture, we have done both logistic regression and Poisson regression. So only difference from a simple Gaussian regression is that you need to apply certain transformations because the parameters of interest are restricted in their parameter space. So for example, the theta parameter in the Bernoulli likelihood is strictly between 0 and 1. The lambda parameter for the Poisson regression is greater than 0. Okay. So we need to apply certain transformations which changes the scale of the intercept and the slope, and that's how we see this kind of effect. By the way, one more thing you can do is that you can back transform the estimates of intercept and weekday to get actual number. So basically number of road accidents or the actual effect. So how much is the difference in actual number of road accidents between weekend and weekday as estimated by the model, right? Because this you are getting is log of that number, right? If you want to get actual number, you should do something like this. Basically, you can get posterior samples. Okay, so your model M3, you can retrieve posterior samples from M3, right? And what posterior samples you are interested in? You are interested in estimate of alpha and beta. This is estimate of alpha. This is estimate of beta, right? What I am going to do with alpha and beta? What I will do is I will apply this. I can obtain number of road accidents during weekdays, because during weekdays the value of this predictor weekday will be 1. So that means I just need to add alpha plus beta into 1, right? So that will be accidents during weekdays, and of course exponent of this whole thing. Okay, so this will give me the actual value of lambda during weekdays. And what will be value of lambda during weekends? So actual number of road accident during weekends, or basically actual rate of road accident during weekends, will be exponent alpha plus beta into 0, because during weekends the value of parameter weekdays, the predictor weekdays, 0. So it is just exponent of alpha. So if I take difference of these two, accidents during weekdays minus accident during weekends, okay. Now this gives me the road difference in road accidents on weekdays versus weekends. Now you can basically describe, you can retrieve the 95% credible interval of this estimate. This is still estimate. This is not a raw number or observed number. This is what your model is estimating, right? Given this model, this is the difference in road accident, rate of road accident on weekends versus weekdays, right? So what you are getting in the model output was on log scale. So you are getting log lambda, right? And the difference of log lambda across weekend and weekdays. Now you are getting the actual difference between lambda value in weekend and weekdays. This thing will give you 95% credible interval of that, right? So this number shows you actual difference in road accidents, value of actual difference of lambda between weekdays and weekends, the parameter lambda. So it's not on log scale anymore, it's the actual scale of parameter lambda, which is the underlying rate of road accidents. Okay, so this is called back transformation. So a model was set up in a particular way because we applied some transformation on our parameter. Now we have back transformed it to get the actual value of the parameter. Okay. So sometimes you might be interested in actual value of the parameter because we had a parameter lambda, and if your theory has certain predictions about the parameter lambda, or let's say parameter beta, whatever the actual difference between weekend and weekdays, then you can back transform it. Okay, so sometimes it's really useful to visualize how much is the effect. So this tells you the actual effect. So the difference between weekend and weekdays is somewhere around 90. Okay, so basically on weekdays there are 90 more accidents than on weekends. That's what this tells you, right? The estimate of beta from your model summary, this was on log scale, so this is not really interpretable. Basically it's 0.98 to 1.01. How would you interpret how much is the difference between weekend and weekdays? It is this, right? Because it's in log scale, so it's less interpretable. But this particular value is pretty much interpretable. So this much is the difference between weekdays and weekends in terms of number of road accidents or the underlying rate of road accidents. Okay. All right. So I'll stop here. In the next lecture, we will practice a bit more. Basically the regression modeling, but for a more realistic example using a log normal likelihood. Okay. All right. I'll stop here. We will meet in the next lecture. Thank you.